our first speaker is Professor Sergei Gukov. The introduction. Well, actually, all the other speakers need to introduction. So Professor Gukov worked on various topics of the research, like the field theory and the mathematics, topology, and even neural network. So actually, he can give any neural talk. But today, he's going to tell us something about pH fields and the categorification of quantum invariants and street. Yes, sir.
Yes, thank you very much. Thank you, Wenbin, for a very generous introduction. I want to start by thanking all the organizers, and there are many of this amazing event, for bringing us here so that we can enjoy cultural, mathematical, and other parts of the program. I also probably owe you apology because this is very broad audience, and there are experts in the audience to whom most of my talk will be known or familiar or fairly elementary, perhaps. But because audience is broad, I had to pitch it somewhere in between. So I apologize if it's also too advanced for beginners, so it's hard to place it right. And first half of the talk is going to be pure mathematics, whereas only in the second half of the talk we'll reach some kind of physics and not much. Indeed, this is supposed to be mathematics of, I don't know, string theory or physics related. So I apologize if there is not enough physics in this talk. What I'll try to do is give you overview into research that has been going on for past couple of years. This is aimed to develop new invariants of 3 manifolds and 4 manifolds. So the name categorification is aiming to get us closer to the realm of understanding smooth, exotic 4 manifolds. I probably won't be there yet, but again, my goal is to sort of set the stage, and hopefully it will be useful even to some later talks in this session and perhaps in other sessions. There are many ways to tell the story, and my focus will be from very particular angle, which will emphasize the relation between vertex algebras. These are mathematical constructions responsible for symmetries of conformal field theories in 2 dimensions, on the one hand, and another area from quantum algebra, namely quantum groups. So these 2 subjects, quantum groups and vertex algebras, have long-going connections. So these are areas that have already been established and connected in 80s quite extensively. And typical connection goes roughly the way it's illustrated on the slide, that you can consider braiding operation in the context of, say, topological quantum field theory associated with quantum group. And then the same braiding operation can be realized as half monodromy of vertex operators in vertex algebra. So this kind of relation is very central to old connection between vertex algebras, VOAs, and quantum groups. So in this talk, we'll do something quite different. So that's why I want to mention that there is this old relation, and it's going to be relevant to us, but there will be also completely new connection. So the modification from this talk, from this old perspective, will be that the kind of representations that we'll be considering, the representations of quantum groups, will be infinite dimensional. So usually in the connection I just mentioned, the way things are understood, this sometimes goes by the name of Kazhdan-Lusztig correspondence, this categorical version of relation between quantum groups and vertex algebras. So usually people formulate it in a finite dimensional context, and that's where it's easier to study. But we'll be considering representations of quantum groups, which usually are affectionately called color in the TQFT applications. This will be infinite dimensional representations for us. So that will introduce several complications. First, we'll have to deal with infinities because the name infinite dimensional has infinity in there. Secondly, unlike finite dimensional representations, infinite dimensional ones can have general complex highest weight. So exponentiated highest weight is something that I'm going to call X in the future slides. And therefore, there will be kind of new dependence on this continuous parameter that is, again, absent in a traditional story. But in addition to this new perspective on sort of old connection between vertex algebras and quantum groups, there will be completely new connections that we wouldn't be able to ask in old days. So therefore, one concrete punchline of what I'll try to explain, at least in the first part of the talk, is how this development of new invariants of knots and free manifolds associated with quantum groups and infinite dimensional representations can provide us new hints, new clues about structure of quantum groups, for example, new geometric interpretations of quantum groups, and perspectives on logarithmic vertex operator algebras, which is an interesting subject in its own right. So speaking of quantum groups, this subject, of course, again, has 30-year-old history, so it's a very long, well-established, mature subject. And the picture, if I were to draw geography, would look something like this. For generic values of Q, which for me in this talk will be inside the unit disk, so parameter Q will be in absolute value less than 1, then it's not very ambiguous what we mean by quantum group. It's more or less unique construct. On the other hand, as we approach roots of unity, that's where one can formulate different versions of what one means by quantum groups. In particular, all these questions that I mentioned on the previous slide, such as braiding and so on, can be different in many of these different versions. And this is only a small sample of what we can find in the candy store of quantum groups if we were to try to list all of the versions that we have at roots of unity. So in this talk, I'll be mostly focusing at generic values of Q, but in particular, the new perspectives that I mentioned emerge when we try to take the limit Q goes to root of unity. And that's exactly where we start building new bridges to many things which are actually better established at roots of unity. So there is a kind of dichotomy here that at generic values of Q, as I mentioned, quantum group itself is unambiguous. It's clear what we mean and so on. But its representation theory, the way we'll be interested in it, is more complicated because we'll care about infinite dimensional representations. Whereas as we approach roots of unity, here we have many choices, and there will be more very delicate questions, what we mean by quantum group, what we mean by quantum-listic correspondence, and so on. But many questions, at least in this setting, will be easier because they'll be finite. So finiteness versus infinity is what will be reversed in this process of approaching roots of unity. Yes, right. So I'm not giving here even names. I'm not even attempting it because there are so many things to decide. This is general picture. And by the way, I should say that yes, please ask questions at any point. So I'm going to use this three-dimensional topological field theory as a bridge between these two subjects. So again, there are many different ways to introduce the subject or discuss its aspects. So that's going to be my perspective. And in early days of this invariance, which I'll review for you in the next 15 minutes, mathematical definition was only available for a particular class of so-called plumb manifolds. I'll say what these are in a short second. And the question was, can we extend it to general three manifolds? So this slide or next couple of slides are precisely going to address this point. Can we have definition which is available for general three manifold? So this is based on the famous theorem of Licorice and Wallace and its improvement. So the theorem of Licorice and Wallace says that every closed-oriented three manifold can be obtained as a Dane surgery on a knot or more generally a link. So usually when we do surgery, we remove the neighborhood of a knot or link, then glue it back with some coefficient, and coefficient in general is fractional. But theorem says that with integer coefficients, that's enough. And of course, that's not a unique way to construct a three manifold. So there are infinitely many ways. They're related by so-called Kirby moves. And in particular, this manifold you can construct as -1 surgery on a trefoil knot, plus one surgery on a figure-8 knot, they give exactly the same manifold, and there are infinitely many other knots and links which will give exactly the same three manifold. So they're all related by Kirby moves, which are analogs of Redemeisser moves. So then it turns out, just like this theorem makes actually slightly stronger statement than just surgeries using rational surgery coefficients. It says that integers is enough. There is another way to strengthen it a little bit by saying that you don't actually need to use all knots and links. You can use certain family, which is fairly generic. It's fairly broad family, and it consists of so-called homogeneous braid links. So these are knots and links whose braid presentation is the way I read this picture from left to right, has in slot I, where we have braid generator sigma I, only either positive type of crossing or only negative type of crossing. Both are allowed, but in a given slot, for example, here in the first slot, you see that we have only one type of crossing. So this strand always goes over, and let's call it positive, whereas in this crossing, the other strand goes over, so we can call it negative. Yes, that's the notion of homogeneous braid, or a knot or link which has such presentation is called homogeneous braid link. And a stronger version of this well-known theorem, which is maybe not as well-known, is that you can construct every closed-oriented free manifold by integral surgeries on just this class of links. It's a fairly broad class because until 10 crossings, in fact, most knots and links are homogeneous, have such presentation. So it's not a very strict restriction on the class, but it's a subclass. Okay. So I'm not going to give proofs in the talk mostly, but this actually, proof of this theorem is a good exercise in Kirby calculus. So Stallings has been studying such homogeneous braid knots and links extensively in his work, and in particular pointed out that such surgery representations that we use in Licorice-Wallace theorem can be stabilized by adding additional components, additional surgeries, which don't change the manifold, but bring everything in a homogeneous position. Okay. So the upshot is that every three manifold can be constructed from those. So then next, an important theorem here is that if we take what I mentioned earlier, namely quantum group a generic Q and its infinite dimensional modules, these are called Verma modules. So these are highest or lowest weight representations. If you're familiar with the representation theory of SL2, just classical SL2, think about discrete series representations, for example. So they have either highest or lowest weight, and then operators E or F, Chevalier generators, either take you all the way down or all the way up. And Verma modules are essentially like that. So these are analogous representations for quantum group, which have either highest or lowest weight. So here it's denoted by lambda, and they're infinite dimensional. So they go one direction depending on whether it's highest or lowest weight. So in my talk, I'm going to focus entirely on SL2. Everything is believed to be generalizable to general Cartan types. It's mostly worked out at the level of theorems for Cartan types A or SLN, but in my talk, I'll focus just on SL2. Okay? So highest weight is just a single number. It's and as I already mentioned, it's a general complex number, so that's what I call lambda. Exponentiated version of lambda is what I can call x and y. And the point of this theorem is that if we use R matrix, the same universal R matrix from Reshetikhin-Turaev construction, basically, and follow Reshetikhin-Turaev construction, then for this class of knots and links, which are homogeneous, that we discussed on the previous slide, you can define knot or link invariant just basically by taking traces over this R matrix. And the statement of the theorem is non-trivial when it says that it's a well-defined invariant in two different ways. First, you have to verify that it's well-defined as a topological object. So in other words, it's invariant under Redemeisser moves. So that's very familiar to definitions involving finite dimensional representations. But here there is a new ingredient, and that's actually where most of the novelty goes. Because we deal with infinite dimensional representations, these traces the sums here involve infinite ranges of summation. So we have to show that the thing is well defined as a Q series, for example. And that's actually the place where the homogeneous condition is being used. Okay, so it involves non-trivial combination of topology and representation theory, which reduces these diagrams to racetracks and highway diagrams and so on. I'm not going to talk about it, but I want to point out that well-defined here means is actually a very strong loaded word, which means two different things. Well-defined topologically as invariant and the Rademacher modes, and well-defined also in terms of infinite dimensional. Okay, so this is probably the heaviest part of this machinery. Once you have this defined for class of nodes and links from which you can construct general manifolds, then you basically can use a very Sergei formula to That's a very good question. I don't think it's been explored at this point, but again, everything can be just defined in the universe of in surgeries on this homogeneous braid knots and braid links. It's a very good question to try to extend it further. So again, it hasn't been done, but I think it's a good question. Yeah, thank you. Any other questions? So if this was too complicated, this was general theory. Everything can be made more combinatorial, and that's how things were in early days of the subject, where if you have a knot or a link which consists just of unknotted circles linked in a chain analogous to the Hopf link, as illustrated here, then every such link presentation can be encoded in the data of graph whose vertices are decorated by integer coefficients. These are precisely the Sergei coefficients that are being used on each component. And then everything becomes very diagrammatic. For example, you can encode the data of such decorated graph in its adjacency metrics, and Kirby moves or the invariance under this topological moves that I mentioned becomes more fun. For instance, there are these operations called blow up and blow down, because same type of Kirby diagrams are also used to label four manifolds, and in connection between four manifolds and complex surfaces, these are really blow up and blow down operations, where at the level of a graph, you're allowed to add a vertex or remove a vertex, but in a very particular way. For example, if you add the vertex labeled by ±1, you have to change the coefficients of other vertices in a correlated way, and these are so-called Kirby moves, or in this context, Kirby-Neumann moves. No, these are sufficient conditions. Again, that's correct. So indeed, same data, exactly same data is used to construct four manifolds, for example, same plane diagrams, but the set of moves is different. So these are three-dimensional Kirby moves that, from the perspective of a four manifold, don't change the boundary of a non-compact manifold, but may change the interior. For example, this move would change the second Betti number of the corresponding four manifold, whose three manifold is a boundary, but wouldn't change under this procedure. Here, I'm focusing entirely on three manifold perspective in this stuff. Any other questions? Oh, yes, please. That's right. So I'm describing three-dimensional TQFT and this quantum groups and Verma modules, which, if you like complex surfaces, think about three manifold being a boundary or intersection of your complex surface with the sphere of a very large radius, for example. So that's the three manifold we're talking about. but indeed, the same type of data, for example, this graphs, called Planning graphs, can be used to label surfaces, complex surfaces, or form manifolds as well. And that's in particular, that's where the terminology is borrowed. These moves are sometimes called blow up or blow. So again, the version of the theorem, which is a little bit stronger, but the version of the theorem I showed before, this is something that first appeared in our joint work with Dupay, Pavel Putrov, Kumran Vafa, and was improved in many different ways, most recently by very nice work of Yua Murakami. So it says the following, that if you take this construction I outlined, in this particular class of, let's say, Plum manifolds, in fact, they need to be what's called weakly negative definite. First, easy to verify statement is that this object converges, this result of the surgery applied to this link invariant converges in variable q in the parameter q inside the unit disk. So just in the domain that I outlined in the very beginning, it's a well-defined convergent object. It has integer powers and integer coefficients if we expand it on q. So this is important for categorification program, to which I'm alluding in this talk, but I won't discuss it in great detail, and maybe until very end. And most importantly, it's also invariant under this Kirby-Neumann moves. That's a very important, more serious part of this theorem, because it basically says that it's also well-defined, not only as an analytical object, but as a topological object. So it's actually is an invariant of free manifolds. And then we slowly transition from the definition part. So I showed that it's well-defined in every sense of the word, topologically and analytically. But now we transition to its properties. And fun properties that were sort of expected is that as we take parameter q to a root of unity, we recover some of the familiar invariants. And that's where basically the fun begins. So some of it was reasonably expected, because if you start with a definition that involves quantum groups at generic q and take q to root of unity, surely you're going to find something or some invariants of knots, three manifolds were which were defined for quantum groups at roots of unity. But question is which ones? Because as I showed you in the beginning, there are many quantum groups at roots of unity. There are many ways to realize the braiding and run the Reshetikhin-Turaev construction to construct invariants. So which ones do you find? And interesting thing is that you find pretty much all of them. So you find so-called semi-simple invariants, original ones of Koller, Reshetikhin, and Vladimir Turaev. But you also find non-semi-simple ones, such as invariants of Akutsu, Deguchi, Otsky, and corresponding three manifold invariants due to Konstantinov, Yerpotero, Morand, and many, many others. What's interesting and something, yes? That's going to be another surprise. So you basically anticipate a surprise on the next slide, or 2 slides up, yes. Not obvious, but right. So one thing that I kind of didn't emphasize in the previous slides, but maybe I can already mention it here, is that remember when we were constructing this, even at the level of link invariance, there was this complex parameter highest weight, or exponentiated complex highest weight. So if you expand this link invariant in terms of this variable x, its Fourier coefficients are labeled by integers, which is of course not surprising. But this integer secretly is actually spin C structure on a knot or link complement. So it's clear that it's integer. Why its spin C structure is not obvious at all, and I'm not going to explain it. But in our joint work with Chypry and Manolescu, we pointed out that that's the case. And at that time, it was sort of a bit of a surprise. It wasn't quite clear why spin C structures appear. In other words, what I'm describing to you is not really honest TQFT, but it's a decorated TQFT. It assigns graded vector spaces to surfaces equipped with spin C structure, numbers to three manifolds equipped with spin C structure, and so on. And this could be viewed as a bit of a headache, but it's actually a blessing in disguise, as I'm going to tell you later. In particular, there are quite a few invariants which in low-dimensional topology we care about, which are also described by such decorated TQFTs, where there are these decorations present and play a very important role. So in particular, spin C structure is a lift of a spin structure on the three manifold. And if you play this game and take the Q to various roots of unity, you can find, first of all, decorated TQFTs that I already mentioned, or you can derive invariants which are not decorated by anything. For this, you just have to average over spin C structures. But if you don't, then you can recover interesting other invariants which are decorated by spin structure. For example, Rohlin invariants of three manifolds are labeled by spin structures, and you can recover them by not forgetting this information. So depending on what you decide to either average or not average or do some partial averages, you can recover different types of invariants in this geography plane. Okay. So that's how you can see quite directly connections between different types of invariants. And for instance, Akuchi, Deguchi, and Otsky, they constructed invariants of links using R matrix technique. I mean, this was improved by or highlighted by Murakami. And you can actually directly relate R matrix construction that I outlined to R matrix construction of their invariants and see essentially in front of your eyes what happens as Q approaches roots of unity, how the expressions behave, and so on. So in that sense, what I'm describing provides a bridge between different values of Q, such as generic ones, as well as different types of braiding at roots of unity. Okay. But now we come to more surprises. So for example, another set of invariants which are labeled by spin C structures are so-called correction terms of Higgs-Floer theory, which was introduced by Peter Ostwald and Zoltan Szabo. And these are rather delicate invariants. So Higgs-Floer theory and correction terms were heavily used in various important proofs, such as they gave new proofs to Donaldson's diagonalization theorem. So that's about smooth structures on four manifolds, as well as Thom conjecture, which is about embedded surfaces, genus of embedded surfaces in four manifolds. And these are really interesting invariants in the sense they indicate that, yes, we can actually use this to say something meaningful about important questions in low-dimensional topology. So another bridge that what I'm describing to you is building is a bridge between quantum topology, where we start with quantum groups, construct this quantum invariants, and interesting questions in low-dimensional topology, which really probe something that we care about, such as smooth structures on four manifolds. So why do I tell you about this? Because if you ask about behavior near Q equals 0, so in my geography diagram, this would be the point near Q equals 0. That's where the expansion starts if you think about this invariance as power series expansions in Q. So we can ask a very simple question. What is the leading power? It's a fractional power of Q. The rest is integers. And this fractional power of Q turns out to be related to this correction terms of Higgs-Floer theory, mod 1. So that's a very nice, interesting relation. And many of the theorems in this subject are of the flavor that you can prove it, at least so far. It has been demonstrated for Planck three manifolds. That's the class I outlined a minute ago, but it's believed to be true in general. So I'll show you several theorems which have the same flavor, that currently it's proven only for Planck, but is believed to be true in general. And for young people in the audience, I think it would be fun to complete the proofs of these conjectures by demonstrating that it holds in general. Yes, please. No, these are not integer coefficients. In simple examples, they are. In general, they don't have to be. But as your question anticipates, we expect, and in some cases can even construct, and this talk I'll show you kind of answer in some cases, how to provide a homology theory such that its graded Euler characteristic gives you this, very much like Hovanov homology for links gives you categorification of the joint. Yes, please. Well, weakly negative definite is a technical adjective. Let me not unpack it in detail unless you want me to. Yes, yes. But like I say, it would be in many of these theorems, this flavor will be that it's proved, such as this theorem for this class of Plum, whereas it would be good exercise. And again, I advertise it as open problem. It's an actual research problem, not just an exercise, to construct the proof in general. And again, if you do it, write a paper. So it's not a simple exercise. Okay. Did I answer the question? Any other question? All right. So right. So we know that at least mod one, there is some relation between this kind of fractional powers or behavior near q equals 0 and correction terms. It would be interesting to give an independent definition of these deltas or understand their meaning better. And aside, so in other words, currently the only way I know how to define them is to compute the whole thing, but then you get the whole Q series. You basically, for each three manifold, you compute lots and lots of coefficients. But if you're interested only in the leading term, I would imagine there should be much simpler, more intrinsic three-dimensional definition. And it would be nice to know what it is. So that's another research problem, which I mentioned here on the slide. That's basically what this is. Exactly, yeah. So that, yes, mod one, they're all related. So that's basically that guy. But question is, what is this not mod one? Because this delta is an absolute number. I mean, once you work with a concrete manifold, it could be something like 15.7, for instance. And the question is, what is that 15.7? Not just mod. Rho would be only mod one. Well, my answer is twofold. Modular one, yes, but not modular one, no. It's much more delicate. Yes, exactly. Yes. Okay, good. So then another piece of work which is probably very useful for understanding, in particular, this problem I mentioned, as well as other questions related to dependence on the spin C structures, is a nice paper by Ross Ahmedchad, Peter Johnson, and Slava Krushko, where they try to understand a little better, again, where it comes from, how this is constructed. So they ask, okay, can we build manifolds which take values in a Q series, which is what we are trying to do, and which exhibit this invariance under Kirby-Neumann modes. And by requiring this invariance under Kirby-Neumann modes, they managed to reduce the problem to one simple equation. So that's why I mentioned here the picture of a Mandelbrot set, because it illustrates that from one simple recursive procedure, you can construct very complicated structures. And here, from one simple recursion equation, they demonstrate that every solution, which is what they call admissible function, leads to invariance of the type that we just discussed. So this is yet another interesting research direction, because it means that potentially there could be lots of interesting free manifold invariants, close cousins of what we just discussed. So it would be interesting to understand what they are, study them more carefully, and so on. So it's interesting on its own right, but also this work highlighted yet another aspect. In the previous slides, I already mentioned some connections to Higard-Fleur homology, for example, via these correction terms. But this work puts it in a further perspective by connecting this recursive equation, admissible function, and the story to so-called lattice homology. This is something that was invented by Nemeti and is basically another description of Higard-Fleur homology in a combinatorial way. So it shows that indeed the subjects are connected much more intimately, and this spin C structure dependence and spin C decorated to QFT nature is not accidental. Well, at this point, this is a hint. So it's what I described to you is not a categorification yet. So there are analogous invariants emerging from lattice homology. That's what they discuss in the paper, which are not, which are decategorified. Even at the decategorified level, it's interesting. And therefore, like I say, there is a lot of potential here to upgrade it to homological level. So that's a very another big question. But even here, it's a fairly rich story. Then there is another connection to vertex algebra. So that's what when been anticipated a couple of slides ago. So we have a form which has q to some fractional power multiplied by power series in q with integer powers, integer coefficients. And that's exactly the same form that characters of vertex algebras have. Okay. So it turns out that for all ciphered manifolds, these are characters of very familiar logarithmic vertex algebras, sometimes actually less familiar than others. For instance, if you go to high number of singular fibers or try to construct them using graphs with several high valency vertices, you have to actually extend the existing constructions of Fagin, Tipunin, and others of logarithmic vertex algebras. But I want to point out that this is a connection. This is exactly this new connection I was alluding to in the beginning, because until you have an invariant which is valued in Q series, you didn't even have a chance to ask this question. So in other words, unless Q is allowed to be generic, we didn't have a chance to make this comparison. And now this is a theorem for, again, some class of manifolds and conjecture that it should be true in general. And it's, again, fun to explore it further. So that's the conjecture, sometimes called 3D modularity. So this, I mean, it's good to understand this conjecture more fundamentally, again, prove it in larger classes, but you can also ask a very baby version of this question. Namely, you can simply ask how fast are the coefficients grow for general manifolds. So this coefficients in the Q expansion that I call AN on the slide. They could grow polynomially with n, they could grow exponentially with n. Well, it turns out that they don't grow polynomially, they don't grow exponentially, they grow exactly as exponential of square root of n. And in vertex algebras, this is very familiar behavior. This is exactly how coefficients of characters of VOA are supposed to grow. And there is a single number which determines the speed with which they grow. It's called central charge in theory of vertex algebras. Yeah. Well, AN are coefficients of these invariants, Q series invariants, which is what I'm describing here. That's correct. So this is the new class of invariants. Yes. So they happened, as when been predicted a few minutes ago, they happen to be also characters of vertex algebras. So this is surprise. It didn't have to be this way. And yes, exactly. Character has to do with the right-hand side. So this relation between topology or topological invariants, which are Q series, and characters is something that was very, very different from this old-fashioned relation between vertex algebras and quantum groups I mentioned in the beginning. We did have a quantum group in the game, which was responsible, which was at a generic Q. We used Verma modules. But these characters are related to quantum groups at roots of unity. So this is completely new and different relation or different type of flavor. So again, it's only possible once we have generic values of Q, then we can ask, can our Q series valued invariant be a character? And it turns out that the answer is yes. Again, to probe this behavior, we can basically ask how fast the coefficients grow. And if we believe that there is such a relation, they have to grow exactly with the speed determined by a single number. So again, instead of asking which vertex algebra it is, which is a lot of information, I can simply compute the invariants and ask how fast the coefficients grow. It's going to give me one number, but it's a very important number for vertex algebra. It's called central charge. From the point of view of low-dimensional topology, it's a manifold invariant. So therefore, for every 3 manifold, we get a number, which is this central chart. Previous transparency. Oh, yes, it's slightly modified. So in this case, CF will be something else. In fact, it will be -1. That's the difference between C and CF. Yes, I apologize. So don't pay attention to C. C is not important. What is important is C effective. It's called sometimes effective central charge. It's slight technical difference where C effective is defined as C modified, it depends, subtracted highest weight of vacuum representation. Yes. So that's the difference between C and CF. Yes, yes, sir. Yeah, so the relation is, just to deconfuse us. So there are two things. So the hat itself is related to VOA, which I actually don't know what this is, but associated to UQ, a generic Q. So Q is generic. And what happens here is that we get relation between this invariance. So this happens to be characters for log VOA, which actually I do know, at least in many cases, and that by Kazhdan-Lusztig correspondence is associated to quantum group at the root of unity, but non-semisimple. So non-semisimplicity that we mentioned in a very, very different context earlier in our discussion. Yeah, so Vanya is pointing out that there should be more connections here to double affine Hecke algebra. Yes. And I don't object to that. In fact, I like this point. No, it's not rational. It's oh, sorry. I was going to explain something else. Yes, thank you. So that, yeah, in observation in the previous slide was that it's a character of logarithmic vertex algebra. It's not rational. Yeah. So now I was going to explanation of something else. That when VOA is rational, this is a theorem. That's why I put the slide here. That this behavior, which we often attribute to John Cardy in the subject, is a theorem in rational VOA. But in logarithmic VOA, actually, there is no such theorem. And for a long time, I myself, when I started studying the subject, thought that behavior should be the same, that coefficients should grow as exponential of square root of n. Okay? That's a very natural expectation. It's just generalization. Why not, right? So it turns out that that's not correct. So next slide is a correct statement. So that's why I was trying to differentiate what's a theorem and what's a new statement. So this is a new theorem, which goes back to our recent paper with Moon-May Jagadale, which says that correct behavior is actually a modified version, and I'll explain where it comes from. So, right. You know, like in number theory, many papers start saying, assuming generalized Riemann hypothesis, we prove blah, blah, blah. So here, if you assume what's called generalized volume conjecture, that's a particular type of behavior, which is something that has not been proved in general, but is widely believed and extensively checked. You can verify that the following holds true. R is a rational number. So n is integer, which is label of our coefficients. And we are again asking how fast it grows. So this formula modifies Cardy growth in two different ways. First, in logarithmic CFTs or VOAs, this coefficient C effective can be, for example, in negative number, real but negative number. So then the square root is already complex valued, but actually more exotic things can happen. So the C effective itself can be complex valued. So you definitely need this modification where you take real part. That's necessary. So this is responsible for behavior which involves oscillation. So usual Cardy behavior is where you have exponential of square root of n, and the graph looks, it just goes straight up. Above, I mean, it's everything is positive. Here, because we take real part of a complex number, it can actually have this interesting oscillations and go down. Another thing which Vanya is pointing out is that there is some rational number R here. I'll explain on the next slide where it comes from, which is responsible for the following. So if you really plot this coefficients an, you see that you don't have a single line as in rational VOAs. That's the picture we have here. So you have several lines, let's call them branches, and the number of such branches is denominator of this rational number. So everything splits. So that's a completely new phenomenon that, again, I didn't expect when I was a newcomer to logarithmic. That I don't know. So whether this R would be related to parameter of rational Dachau is a good question. That I don't know, but something one can probably explore. Should explore. Yes, but. No, actually, both C effective and R are determined either by three manifold. That's how story emerged for us. And my question will be, what kind of three manifold invariant is this? And also, what kind of three manifold invariant is this? I'll give a bad answer to this, but I'll actually formulate this as a question on one of the next slides. And then there is a conjecture that in all logarithmic VOAs, you should expect this behavior. So this would be my improved version of conjecture, not just naive one that it's like in old ways, that's not gonna fly. We already know that would be wrong, but that would be my conjecture that in logarithmic vertex algebras, that's the behavior one should expect. Either prove or disprove this. So let me explain what this R is. So first of all, you can try to prove this. So where does the proof of this theorem come from? I mean, even though it makes an assumption of a certain behavior, there are some steps that go into the proof. So the beginning is actually very straightforward. So first, you say that coefficients an, whose asymptotics we want to understand, z hat. Yeah, these coefficients are, for example, for z hat. Oh, sorry, this could be anything, but including z hat, yes. So suppose you have a function whose coefficients an you want to understand. So what do? You can take this function and basically extract the pole, right, of q to the n. So integrate on around q equals 0, this dq over q with q minus n, right? So that's the way to extract the nth coefficient. But then the typical strategy is to push the contour of integration close to the unit disk in the q-plane, hugging the unit disk. So we started in a q-plane with a small circle, and then we can expand it so that it's nearly q equals 1 in absolute value. So that's a strategy that Cardy used, and also a strategy that Ramanujan used. So sometimes it's called Ramanujan trick or Cardy way of proving it. So then what happens is you find that this integral is dominated by a saddle point near some rational value of angle theta. So somewhere here, if this is your angle theta, there will be some rational number. In language of tau, it will be basically tau equals to r, where this integral is dominated. So that's the definition of R in the previous slide. It's basically the saddle point that you find in trying to expand this contour to hug the unit disk from inside. Okay, so that's the value of R. Again, I don't know how to independently, I can give a definition of this R in terms of so-called Stokes coefficients for three manifolds, but it would be nice. I mean, this is just numbers, whereas Stokes coefficients is a lot of data. It's actually hard to compute. So it would be nice to give independent definition of this C effective and R in terms of just invariance of three manifolds. Okay. So I'll have a little bit more to say on this in the next slides, but here is the conjecture that this type of behavior should hold in general logarithmic vertex algebras, something I already mentioned a couple of minutes ago. So that's again a statement of the problem, that please tell me what this C effective and also R is. Based on resurgent analysis, which is where physics enters, you can show that this value of C effective should be related to value of Chern-Simons functional for some flat connection, complex flat connection. So this is first place where gauge theory enters the story. So we started our discussion with quantum groups, with Verma modules and transition to vertex algebras. There was no gauge theory inside. So this is indication that the problem we're discussing has something to do with gauge theory. In fact, this, again, statement that C effective is basically determined by value of Chern-Simons functional, but there are two obvious problems here. First of all, which flat connection? Because generic three-manifold has hundreds and maybe millions of flat connections. So many of them are the same. For example, if you work with the Brieskorn sphere, there could be thousands of flat connections. They all are on roughly same footing. So which one do you pick? How do you pick your favorite child? I don't know how to make that decision. So I don't think I'll have time to explain it. Just at this point, but I'm trying to explain the problem that I don't know how to solve. That this is Chern-Simons value of some flat connection, and I mean, we can determine which one using Stokes coefficients, which is a very complicated way to compute it, but there should be an easier answer. Another problem, which is also quite serious, is that Chern-Simons functional, which is classical invariant of gauge connections, in this case SL2 flat connections, is circle valued. It's defined modular integers. Whereas here, we're talking about an actual number. So we actually need a very specific integral lift of Chern-Simons value. This is what I denote by this integer m star. And again, what determines this another integer invariant of three manifolds, other than all this package of Stokes coefficients, I don't know. There should be a better way to answer this question. And in the remaining 10 minutes, I'll try to explain what I mean by this picture and what black swan has to do with this subject. So this is going to be last sort of fun part of the talk, if you wish. So black swans. So for a long time, in fact, until fairly recently in the history of our civilization, it was believed that only white swans exist, until Dutch went all the way to Australia and discovered that there are indeed black swans. So this happened in 1697, so quite fairly recently. So since then, this phenomenon was, or the term was basically applied to any kind of phenomenon where naive conjecture, just extrapolating from what you see in simple examples, is like a white swan, whereas something unusual, something you don't expect, is coined the term, I mean, is termed the black swan. So in some sense, it's anti-conjecture. So usually conjecture is when you take lots of examples and extrapolate the behavior, and anti-conjecture is you take lots of examples, extrapolate the behavior, but still stay so conservative you believe that it's gonna break much later if you expand, okay? So in some sense, black swan is anti-conjecture. So I'll explain what it has to do with our story, but just as a fun remark, so Nassim Taleb, who is a Lebanese-American businessman, so he made a lot of money in financial markets using exactly this kind of idea and popularized the term in the past several decades, where, again, now black swan refers to event which is completely unexpected, but if it happens, it can change dramatically our understanding. Of course, in mathematics, we always should be conservative and look out for such black swans. Okay. So why do I mention this? So I promised that there will be something for physicists. So that's the question for physicists. We often ask, what is the relation between perturbative and non-perturbative theory? Okay. So perturbative theory is well defined thanks to Mr. Feynman. We use Feynman diagrams. We can define its expansion and so on. But non-perturbative theory in general is not defined, despite the fact that subject is mature and exists already for 60 years. I mean, the subject of QFT. So we often ask, what does non-perturbative completion of a given perturbative theory looks like? Very often, non-perturbative completion can be done within the framework of that same theory whose perturbative behavior we're studying, but sometimes it requires a bigger theory. So it's embedded in a larger theory. So therefore, if you ask this qualitative question, given a perturbative QFT, is my non-perturbative completion going to be a bigger theory? This is actually something where resurgent analysis can help. Resurgent analysis is part of analysis, which tries to connect these two subjects by Borel summation of the perturbative series. Okay. Usually, this Borel summation and resurgent analysis is perceived as very technical thing, but here I want to emphasize it can be used for simple qualitative questions. Like, do you need a bigger theory to do non-perturbative completion? This is kind of question that physicists actually care about, and it's a hard question. So that's what I'm asking here. And the way to answer this question, the simple qualitative question, is look at the Borel plane. And if in the Borel plane, we see only the saddles of the original perturbative theory, namely classical solutions to original functional, action functional, or Chern-Simons functional, for example, then yes, we have a good indication that non-perturbative completion can be done within the framework of the original theory. But if we see saddles which are not classical solutions of the original perturbative theory, then it's a good indication that non-perturbative completion is going to require bigger theory. Okay, so that's a simple qualitative lesson. Exactly right. And these saddles, which are not expected, but if they're present, they would indicate that we need a bigger theory. I would call them black swans. Normally, again, in simple cases, you wouldn't expect them, but if they exist, they would qualitatively change the understanding. So that deserves the name of black swan. That's what I'm going to use later on. Okay, so that's basically this question that we're trying to ask. And one simple class of problems where it comes up, for me, it will be related to complexification of Chern-Simons functional, but you can actually try to think about more general theories where this happens. Suppose you have some gauge theory and you do a very drastic operation. You require that your field is now complex valued. So you basically take your connection and add to it imaginary part. What it means is that you immediately made your space of fields, even if it was compact, non-compact, okay? So that's immediately going to be the sort of result of such operation. In particular, now we need to make things well defined or to provide this non-perturbative formulation, we have to say what happens at infinity. If you think in terms of moduli spaces, moduli problem, we would probably have to use some kind of compactification, right? So that's very typical in the way we approach mathematically such questions. We need to add compactification divisor. And as we do, we can introduce new solutions at infinity, and that's exactly where these black swans may come in. They could be saddles or some critical points which are hiding at infinity, right? Which are required when we try to make the problem well-defined and compactify non-compact moduli spaces. So that's exactly the way it's going to appear for us in the context of complex Chern-Simons. In fact, the story I told you so far has very, very long history, and it originated by trying to embed Chern-Simons theory, even regular Chern-Simons theory at the perturbative level, the way Witten described it many years ago, into string theory. So here, we already have a pre-knowledge, if you wish, that yes, this Chern-Simons perturbative theory for complex gauge group will require much bigger theory formulated in terms of stringy things, fibranes, and so on, as its non-perturbative completion. So we should be expecting black swans. And in fact, they do appear. So, right, so that's coming back now to the punchline and to the question. There are indeed, this is a question, can black swans exist or saddle points on a Borel plane be other than complex flat connections for SL2C? And the answer is yes. If you go to complicated enough free manifolds, in simple cases, you don't see it. But in complicated enough cases, for example, if you do surgeries on connect sum of twist knots, then you do see such black swans, which are not just classical Chern-Simons valued of complex flat connections. So another example is a surgery. So here, the knot is a composite knot. It's a connect sum of two, and surgery on it is slightly more complicated. You can ask, can I have a surgery on a prime knot such that it leads to this phenomenon? The simplest knot I know has 12 crossings. So this is particular pretzel knot. So again, you can see you have to go fairly high in complexity of the theory. That's why it was important for us to have all this technology reasonably well developed that we can actually compute it. And then the phenomenon starts showing up. Of course, if we were naive, we could make a conjecture that such things do not exist, but that's again, that would be false. And yeah, in a recent work with Pavel, we proposed that as several candidates with lower number of crossings where this phenomenon can potentially be found, but we didn't demonstrate it. So we gave an argument why for lower crossing nodes, but only starting with only 9 crossings enough such things can be found. But again, the actual one where we prove it as a theorem is 12 crossings. And this has application to a couple of other subjects, but since I'm running out of time, let me skip this and just conclude by saying that I try to outline for you new connection between 3-manifold invariants, quantum groups, and vertex algebras, which relates 3-manifold invariants themselves as characters of VOA. But this is only one perspective, one way to look at the story, and I completely skip many other related developments involving enumerative geometry. I mean, one could give the same talk just from the angle of enumerative geometry, from the point of view of gauge theory, and there is more one could say about mathematical physics, but since time is short, these are the choices I had to make. So thank you again for your attention.
It's covered. If it's something else in power series, maybe in pictures or maybe in some other methodology.
Right. So without speculating too much, I would say that in this context, we do expect invariance, for example, of 3 manifolds valued in rings, modules over rings. This would be closely related to this categorification program. And in particular, this connection to vertex algebras may help it because once we have this z-hat invariant written as a character of some VOA module, then module itself can be a good candidate for such categorification. So that could be indeed higher level structure, but it's a good question whether there is something beyond that. So that, of course, I don't.
Specific locations or this.
Well, that's right. So aside from many different areas of mathematics, that's a homework to figure out where these bridges are. Yeah, so that's actually a very good question. It's more related to modularity properties of this Q series, which is yet another perspective, something connection to number theory could be also put as one of these bridges. So one can explore the space of conformal blocks by performing SL2D transformations and asking what is the modular orbit, for example. So here, it seems that this invariance, Q-series invariance labeled by spin C structures naturally form an orbit, but often it can be viewed as a suborbit of something larger. And that would be precisely the space of conformal blocks for these log VOAs in this context. So many people are exploring it, and it's a very rich story, but my feeling is that it's still, again, in the middle of exploration. So there are many more things one can do. And I'm not really an expert on it. People like Miranda Chang or others, but actually Anton maybe in his talk later today shed light on some of such questions. Anton Milish. I think Oleg had a